Welcome everyone. We are Group 35 and our project title is Anime Recommendation System. The objective of our project is to develop a recommendation system that can efficiently suggest animes to the user. For this project, we took assistance from the following research papers. The first research paper is the Neural Collaborative Filtering, published in the WWW conference in 2017. It first presents a probabilistic model that emphasizes on the binary property of the implicit data. It is then shown that matrix factorization can be expressed and generalized under the neural network collaborative filtering. To explore deep neural networks for collaborative filtering, the paper then proposes an instantiation of NCF using a multi-layer perceptron to learn the user item interaction function. Lastly, the paper presents a new neural matrix factorization model which ensembles a matrix factorization and MLP under the NCF framework. The second research paper is the relation-based collaborative filtering published in IEEE Transactions on Knowledge and Data Engineering in January 2023. This paper proposes a novel deep neural network called relation embedding with dual attention, that is REDA, to cope with the limitations regarding the item similarity. For the dataset, we are using the anime recommendations dataset from myanimelist.net. The dataset contains information from 73,516 users on 12,294 animes. It contains the anime list per users, including dropped, complete, planned to watch, currently watching, etc. It also contains the ratings given by the user out of 10 to the animes that they have watched completely. Now, as our model requires the dataset in different format, we had to pre-process the data in order to train it on our models. In the relation embedding with dual attention model, we needed to alter the data to only include users who had given more than 5 ratings. Additionally, we classified ratings greater than 6 as positive feedback. In the neural network model, we required several features such as name, genre, type, episodes, ratings, etc. to train the model on our neural net. Here we present the flowchart of our project. In the first part of the flowchart, we have shown the architecture of the REDA model. In the model, we first create multiple decomposed embeddings, that is breaking each item into different parts or features to better represent it. We then create a pairwise interaction layer to represent the relationship between items based on different aspects of each item. Each decomposed embedding vectors represent a different aspect of the item. To represent the relationship between two items, we use a pairwise interaction layer. After that, we use dual attention technique, that is memory attention as well as weight attention, to create the item relation embeddings as well as the relational user embeddings. These embeddings are further used to rank the items on their likelihood to be amongst the top K favorite animes of the user. In the second part of the flowchart, we have shown the neural network based model. The generalized matrix factorization model is a variant of the matrix factorization that can be recovered using the neural collaborative filtering framework. In the GMF, the mapping function of the first neural network layer is defined as the element-wise product of user and item latent vectors. The output layer uses the sigmoid function and learns edge weight from data with the log loss. The multi-layered perceptron is used to model interactions between user and item latent features. We have also created a new neural matrix factorization model which ensembles GMF and MLP under the NCF framework. Now we have also adopted the leave one out evaluation strategy. That is, for each user, we hold out one liked item for testing and use the remaining for training. All the items are ranked for user. The performance of a ranked list is judged by the hit ratio and normalized discounted cumulative gain, that is NDCG. The hit rate intuitively measures whether the test item is present in the top n in the list, and NDCG accounts for the position of the hit by assigning higher scores to hit at top ranks. We calculated both metrics for each test user and reported the average score. We evaluate recommendation performance based on HR, uh, for the top n ranked item as well as the NDCG for the top n ranked items. Both metrics are widely used to evaluate recommendation systems. The result reported are the average scores for all users in the testing set, where the HR at N indicates the percentage of users who have been successfully recommended, and NDCG for top N ranked items measures the ranking quality of the positive item. Now we have shown the results of our implementation of the neural collaborative filtering model. Here we see the hit rate as well as the normalized discount cumulative gain for different number of latent factors for top 10K ranked items. We see that the hit rate is increasing as we increase the number of latent factors and is maximum for 60-fold number of latent factors, that is 0.724. Similarly, for 32 and 64 number of latent factors, we see that the value of NDCG is the highest, that is 0.453 and 0.450 respectively. Here you can see the plots for the same. Now we have also shown the results of our implementation of the relation embedding with dual attention model, that is the REDA model. Here we see the hit rate as well as the NDCG for top 5 ranked items as well as the top 10 ranked items after training the dataset on the REDA model. In this figure, we further inspect how each module of the REDA model affects the recommendation performance. We can see how if we remove any module, the performance drop from the complete REDA model. By removing the pairwise interaction layer from REDA, we can obtain a simplified version of the model without PI, in which we only have one embedding for each item and one interacted vector for each item pair. We also remove two critical attention mechanism in dual attention layer and obtain two base models named without MEM and without WGT. We use interacted vector as relation embedding in model without MEM and compress all item interactions using average weights in model without WGT separately with a two-layer MLP and obtain model REDA MLP. We observe that the complete REDA improves without MEM for at least 8% and REDA MLP for at least 5% in terms of both metrics, showing that memory attention layer is a key component for REDA in refining relation embeddings. Moreover, REDA performs consistently better than without PI and without WGT in all settings, meaning that multiple decomposed embeddings and weight attentions indeed capture different latent item aspects and their importance more precisely. This figure shows the experimental results of both models compared to each other, where we present the improvement degree of REDA over NCF on different group of users according to the number of items they interact with. It is obvious that REDA outperforms NCF increasingly as the sparsity intensifies, that is, the number of likes decreases. NCF can achieve comparable performance as REDA, but will drop rapidly when data becomes sparse.
So this is the model for our paper 2, which is REDA. These are several layers in the model, which consist of multi-decomposed embedding, interaction layer, dual attention, and all relational user embeddings also. So this is the go through. This is our implementation of first paper of neural collaborative filtering that consists of two models, GMF and MLP model. Here is the main part, and the implementation of GMF model is here as mentioned as described in the paper. This is the implementation of MLP.
Thank you.